started with this at the beginning of the lectures, but decided not to do things that way. So yesterday I also argued that once you turn on G Newton, so it's not 0, which then allows me to set it to be 1, then the natural observables in asymptotically flat space are S matrix elements. And so, we had some picture, where there's some sort of mystery going on in here, and then we had particles, that were labeled in the way we usually like to label particles going in, and then we had some other particles going out, and then we were computing transition amplitudes between them. And we figured that there was a linear map acting on the ingoing states, which then we could project onto the outgoing states and take the square to get the probability of seeing the out state given that you solve the in state. So in this language, of course, by unitarity of evaporation, I just mean that this S is a unitary operator. Actually, you can convince yourself that in order for these probabilities to make sense, to add up to 1 for any choice of initial state, then it has to be unitary. So at least unitarity is something we can formulate just as a property of the S matrix. Okay. In describing, we'd like to be able to say a little bit more about the S matrix just beyond just the statement that it's unitary. And in doing that, we have to first say a little bit more what this picture looks like for the actual experiment we're interested in, which is the experiment with creating a black hole. So far we've been drawing this picture where you send in this shell of photons. Maybe I'll send it in lower. There's some horizon that forms here. Eventually the horizon goes away, and we're left back with Minkowski space. So that's after the black hole has completely evaporated. That's a horizon there. And then the way it evaporates is that all along here there's Hawking radiation coming out. So this is an S matrix element, right? We fix some initial state, and then we can look at the projections onto different configurations of the Hawking radiation. And indeed, if we take this initial state and we just act with the S matrix, then it generates for us some quantum state up here on some sort of very late time slice. No, so in general it actually won't be, right? I mean, I should be. So here I'm describing what things look like from the outside. So I haven't actually tried to draw the interior region here. You can, so I could try and do something like that. But for now I'm just trying to describe the S matrix, so then it doesn't really matter what's going on behind the horizon.
Just in terms of this picture, will the horizon actually be coming out and crossing the shell rather than?
Yeah. So remember the picture that I was drawing before. So before I knew about evaporation, I was drawing this picture. And the shell comes in here, and the horizon goes like that. So you see the shell goes in after the horizon forms. So that's what I meant by. I guess I didn't really draw it very clearly, but maybe I can go. I mean, of course, the time scale separating these is much smaller, than the time scale at which the mass is changing. Okay. So in this, given this final state here, this configuration of the Hawking radiation, it's often convenient. So I'm going to erase the middle lines here, and let's just say that some color. So this here is the sort of Hawking cloud coming out in the Penrose diagram, and it's convenient to just divide it in two. So just pick some time it's sort of a retarded time because it's a time at null infinity, but pick this time and then just split up the Hawking radiation into an early part and a late part. And I'll call the early part R, and I'll call the late part BH. Okay? And as you can probably guess, R stands for radiation and BH stands for black hole. And the idea is that if we were to trace this back, then what would happen is we'd get to the black hole at some time, and then some of the radiation would have already been emitted, so it would already be in the Hawking radiation. But some of it would have not yet been emitted, and it would still be inside the black hole. So roughly by looking at this decomposition of this slice, we're looking at the decomposition into the black hole and the radiation at some earlier time. But by doing it up here at future infinity, it's clear that it's really something about the S matrix. So it's something that has to make sense. Whereas, if I just said, oh, there's some black hole here and there's some radiation, then we could quibble about how exactly I'm making the separation into the two. So I think this is a more rigorous way of thinking about it. So then, and then we can study, for example, how does the reduced density matrix on BH and the reduced density matrix on R depend on where I put this decomposition. So I can write this more formally. I take the Hilbert space of the outstates here and I decompose it into a tensor product of what I'll call the black hole and the radiation. Although really that both are in the radiation, but the names are sort of what they conceptually mean. Okay, so now one thing that we really like to compute in the context of this decomposition is the entanglement entropy in Rob's language, or just, well, so remember the whole thing is in a pure state. But if I look at the reduced density matrix on either this or that, it'll be in a mixed state, and that'll be because of entanglement between the black hole and the radiation that's already come out. And I often like to compute the von Neumann entropy of the radiation, or Rob would call it the entanglement entropy, as a function of time. So a time being where I put this decomposition. So let's think about what we expect this function SR of t to look like. Well, the first comment is that for the reasons that Rob was saying, actually this SR of t is infinite because this state is the state of the quantum field theory. So then there's short distance entanglement just right around the barrier here, which we want to subtract, or which we don't really think of as coming from entanglement between the black hole and the radiation. It's just coming from the short distance physics of quantum field theory. So to deal with that, there are various things you can do. Rob has been talking about some of the things you can do. What I'm going to do is I'm just going to define a renormalized entanglement entropy. So I think, as far as I know, well, let me finish writing the definition and then I'll comment on it. So what I'll do is I'll take the actual entanglement entropy here in the state that I got coming out of the black hole, and I'll just subtract from it the entanglement entropy of the same region just in the vacuum, so in the empty state with no radiation coming out. And this is called the renormalized entanglement entropy. So yeah, I think the first place that I saw this done was in this paper by Holger, Wilczek, and Larson, but I'm sure somebody has probably done it before that. Yeah. These are just names. So I'm defining the renormalized entanglement entropy, so I wrote REN here in squiggly brackets. Sorry, my handwriting is terrible. I should have apologized for that sooner. So this is squiggly REN close bracket. And then I guess to be consistent, I'll put a bracket here too. So then this is the entanglement entropy in the vacuum. So I wrote VAC, VAC, in the same region. Okay. And then the thing that we want to plot is this SR as a function of time. So let's think about what it does, or what we expect it to do. I'll write the renormalized here too, but I'm probably going to forget to start writing it soon. Start forgetting to write it soon. So the black hole, so the black hole starts out in a pure state. So t equals 0 is when I put the division here, and then there's essentially nothing interesting going on in the radiation. It's just the vacuum because no Hawking radiation has come out yet. So since this is in a pure state, it'll start out at 0. Now, it may not be completely obvious that that's true because of this renormalization. Rather, I mean, it would have certainly been true for SR if it were actually in a pure state. But there is this issue with the short distance entanglement. I'm not gonna try and be really careful about this. But the way this definition works is that your intuition from what the entanglement entropy should do if you forgot about the short distance correlations will end up being correct for the renormalized entanglement entropy. So indeed, the radiation being pure means that this will start out being very small. It won't quite be 0 because of the sort of arbitrariness of this subtraction, but let's just say that it's 0.
Sorry. Can you give me a magnified picture of the t is on future infinity and you continue its light coming back? Where does it hit?
Okay, you want me to draw the picture here in a bigger version? That would help?
That would be fine.
Okay, so the shell went in here. The Hawking radiation, I guess the last Hawking photon came out here. So maybe I didn't quite draw that. Oh, I think I did. Maybe the first one came out here. So then there's this cloud of Hawking photons, and then I'm just splitting that up on a null surface into the. So then there's a part of this state which I'm calling R, and then there's a part of this state which I'm calling black hole. So t equals 0 is here, is this. That's t equals 0, that's t evaporation. Okay? So then what should happen is that SR should start out being small at t equals 0, and then eventually at the evaporation time, it should come back to 0, because once this gets up to here, then R is just the whole Hawking radiation, and now it's again in a pure state. So that's where we're using the unitarity of the evaporation process. Okay, so we figured out what it does in the end, and actually my goal for the next 20 minutes is to justify what I think, or really what Don Page argued, should happen in the middle of the diagram. So the claim is that this is some entropy. It should get up. So it should start growing linearly. It should go up until it gets to some entropy, which is of order half of the initial coarse-grained entropy of the black hole, meaning the area of its horizon, and then it should turn over and come back, and not quite symmetrically, but not that unsymmetrically. So this curve, the plot of this as a function of time, is called the Page curve of the black hole. And so an interesting comment that Andy Strominger made at Stanford last year is that he thinks that being able to compute this curve in some theory is what it means to solve the black hole information problem. So you haven't solved the black hole information problem until you can really compute this curve, and see that it does this, and know what it's doing over here instead of somewhere else. So I should say that we have theories where, in principle, we think that we would be able to do this, and that maybe if we had a quantum computer, we could simulate those theories and compute something like this. But in black hole examples, we don't have examples where we can really compute this. Here, one sec. There are special cases which aren't black holes, but which are like them in 1+1 dimensions, where you can actually analytically compute this. And you can see explicitly how this renormalization works. So I gave a reference in the notes for that. I think it's, if you're worried, for example, about this subtraction, or if this is what really goes on, then solving this 1+1 dimensional example is very helpful, just to convince yourself that this actually is what the picture should look like. Yeah.
So I was a little confused as to how to make this picture compatible with the fact that it should be reversible. It's a unitary process.
Well, so yeah, so I had a rant about that in the notes, which I probably won't have time to get to. So this is not a typical state because I made it in a narrow shell. So the typical state of a black hole, the typical state in the ensemble, whose dimensionality is e to the a over 4, is a state which you build up slowly over a time of order m cubed out of, quanta whose energy is of order the Hawking temperature. And that has to be the case because any state which is typical in an ensemble is going to be time symmetric on a coarse-grained sense. So yeah, that's the arrow of time problem of black holes. So that, I chose some special initial state here.
Why is that S over 2?
Yeah, because so the intuition for this is just you start with some big black hole. So it's actually in a pure state, so its entropy is 0. But if you didn't know that and you just looked at it, you would give it a coarse-grained entropy, which is S naught, which is its area over 2. Now, as the black hole evaporates, it gets bigger. So remember, this entropy is all entanglement entropy. Okay, so the largest the entanglement entropy can be is just the dimensionality of one of the two systems. And so by this time, the black hole has already sort of halfway evaporated. So then the entropy of the remaining black hole is going to be smaller than the original black hole. But you actually should, the 2 you shouldn't take too seriously. It's some order 1 number it's not 1. That was the only real content of that. Yeah.
But this process, it is microscopically reversible, right?
Yes, of course.
Okay.
Yeah. Well, yeah. It should be. Yeah.
At the final stage, the entropy will be radiation entropy will be 0.
Yeah. Of course, because once all the radiation has come out, we're assuming that we started in a pure state, so we end in a pure state. So the von Neumann entropy of the whole Hawking radiation is 0.
But the radiation contains the information, and then the coming outside and stays somewhere.
Well,
Stays somewhere.
yeah, of course. So in a pure state, there's information, right? But its entropy is 0. This is just some, to decide what you mean by information. But yeah.
So this the infinity that is inherent in this entanglement entropy, is that the infinity part is time-dependent?
Is what?
The time-dependent, t-dependent?
Well, yeah. Yeah, I would say, essentially it is because, right, you've got some, in the Hawking radiation, you're decomposing it, but you're decomposing it, so it's not really clear here, but the S2 is sort of getting bigger, right, because you're getting a bigger and bigger cloud. So as Rob explained in his talk, the divergent piece of the entanglement entropy somehow is in it's proportional to the area, so that's time dependent, I think.
What about this vacuum part?
That also is, because I put in the T there. So you pick the
region.
Yeah, the region is changing also. So yeah.
How about the thermodynamic second law? The entropy is increasing.
That applies to coarse-grained entropy. Von Neumann entropy is conserved, right? If you look at a whole system, the evolution is just unitary evolution.
That entropy is not conserved.
Coarse-grained entropy is not conserved. And yeah, I'm going to talk about coarse-grained entropy a little later.
In between the beginning and the end, can I draw a different curve? It is possible, right? What is this?
Yeah. So this is something you compute. So like Andy says, if you have a theory, you can compute this. But at the moment, I don't have a theory. I'm just drawing pictures. So I could have.
Yeah.
I'm going to try and argue that this is the right picture now. But yeah, it's you have to compute it. Okay. So maybe I'll. Okay, so now I'm going to talk about. Interesting. Yeah. We'll see an entropy increasing process here. Okay, so I'm just.
To go back to a pure
Only in a closed system. Okay, so this generic situation here, where you have the Hilbert space as a tensor product of two things, is called a bipartite system. So now finally we're going to do some quantum information theory. So I'm just going to study in general for a moment. So forgetting about black holes, I have some Hilbert space which is a product of two things, so without loss of generality, I'll take the dimensionality of A, which I write like that, to be less than or equal to the dimensionality of B. Now we say that this system is maximally entangled. So the state, so rho AB is max entangled if we have rho AB is pure and rho A is the identity operator on A, which I'll write as I sub A, divided by the dimensionality of A. Okay, so that should not be a surprising definition to anyone in this room, I guess. So yeah, in this situation, we say that the state is you have maximal entanglement present in the system. So now there's a theorem about this, which is due to Page, so it's called Page's theorem. And of course, Page was proving his theorem because he was curious exactly about this decomposition and trying to plot the Page curve. But I'm just going to express the theorem abstractly, and then we'll apply it to the black hole. So what Page says is that so a random psi AB, so a random pure state in the Hilbert space AB is typically very close to maximally entangled. Okay? So, at least for some people in the room, this is probably completely obvious. This is essentially what I guess Renato was using when he was talking about decoupling in his talks last week. I'll go through it in a bit more detail than he did, just because I think it's sort of a fundamental fact in quantum information science. So it's something that everyone should really be comfortable with. Yeah?
What is the probability distribution that you?
Yeah, so so this is not quite the statement of the theorem, because there are things like very close and typically that need to be defined more carefully. So that's what I'm going to do now.
What is that object, sigma A?
This is rho A. This is I. Yeah. You know, I got a C in handwriting when I was in second grade.
See, I was the only one who had temerity.
Yeah. Yeah, that's an excellent question, Paul. Really, yeah, you're really adding something. Okay, so now I should say. Oh, I forgot one modifier here. Provided that the size of A over the size of B is less than 1, considerably less than 1, and we'll see more, So the vary here is going to have to do with the this ratio being small. Okay. Entropy has decreased. So I have to define two things. So first I have to say what's a random state. Okay, well there's one obvious way to make a random state, which is to take your favorite state, which I'll call psi naught. So just some state that you like, and then you act on it with a random unitary matrix. And now you choose the U from the Haar measure, the group invariant measure on the unitary group. So then you can compute, given this state, you can compute rho A of U. Okay, so that's some function, and then you can average this over U to figure out sort of what's typically going on for the reduced density matrix on A, which is the thing that we want to say something about.
Sorry, what is averaging over U? What are you integrating?
Yeah, I'm going to integrate because so there's some probability measure on the space of unitaries, which is the Haar measure, and I'm going to integrate over it. Okay, so that defines what I meant by a random state, and it also defines what I meant by typically. But I need to now define very close. So there's a standard way of doing this, which, again, I guess probably most people here know. It came up in some of the talks already, which is you define the distance of states in Hilbert space by using the trace norm. So for any operator, let me see, very close. So for any operator M, you can define its one norm as the trace of the square root of m dagger m. Okay, and more intuitively, so if m is diagonalizable, then this is just the sum of the absolute values of all of its eigenvalues. Then the trace norm distance between two quantum states, rho and sigma, I don't know, we could call it like d1 of rho and sigma, is just defined as the trace norm of rho minus sigma. And this is a good definition because, so in particular, say you have two states, rho and sigma, and their trace norm is less than epsilon. The trace norm of their difference is less than epsilon. Then without too much trouble, and I think I put it in a footnote here, you can convince yourself that the probability distributions for any experiment differ between these two ensembles by at most epsilon. So if this is less than epsilon, then they're really operationally close. I actually don't like to put the 1/2 there. I know some people do, but no, because whether I call it epsilon or epsilon over 2 is irrelevant, right? Yeah. Okay. So now I'll also be interested in a sec, so I'll just define it now. In the L2 norm, which is just switching the trace and the square root. So now it's trace of m dagger m square root. So then, so this one is somehow the sum over the eigenvalues in absolute value, and this one is the square root of the sum of the squares of the eigenvalues. Okay, so these are two different norms. And I'm going to need to use a fact about them, which, if you don't already know it, I told you to prove on the homework, which is that the 2 norm of m is less than or equal to the 1 norm of m, which is then less than or equal to the square root of the dimensionality of the Hilbert space times the 2 norm again. Okay? So these are some facts which I guess probably some of you know in your sleep, but in case you don't, they're true, and you can have some fun trying to prove them. Okay.
Somebody said Cauchy-Schwarz.
Yeah. So this one is Cauchy-Schwarz. This one you have to think a little bit more. Okay. So I think. Okay. All right, so yeah, now with this technology, we can give the precise statement of Page's theorem, which is that the integral du of the trace distance between rho A of u minus, well, okay, here you are, Paul. So the average trace norm distance between rho A and IA, as we average over the unitary group, is less than or equal to, okay, so here's one version of the bound. Okay, so this is not quite the theorem that Page proved, but it's morally the theorem he proved. I'll tell you what he actually proved in a minute. Is that this is true with no restrictions on the dimensionalities of the Hilbert spaces, other than that A is less than or equal to B. This is the only assumption. Although I think actually that maybe isn't even an assumption. Yeah, no, I think actually I don't even need to assume this. I think it's just true. What?
You're just not claiming.
I'm not claiming any. It looks.
No, A is bigger than B.
Yeah. I mean, it's without loss of generality, you might say. But no, I picked out A here, so that. Yeah. Okay. And this is proven in the notes. But let's just convert. We can see that this does that, right? Because we're looking at the. I think I maybe have a. No, this is right. Yeah. So it's saying if you look on average in the ensemble at the difference between row A and the identity, it's typically this. So now let's. So this is less than square root of A over B. So this is just by staring at this function, you can convince yourself of that. Because this makes the numerator bigger and it makes the denominator smaller, so it's okay. So then if B is big compared to A, as I said here, then this is extraordinarily small. So then just looking at a small subsystem, we expect it to be maximally mixed. All right. Okay, the proof of this I'll just say in words. You first look at you square both sides. You move the square inside using Jensen's inequality, which you can look up if you don't know it. Then you use this inequality to turn the 1 norm into a 2 norm squared. So you've got something like the integral of the 2 norm squared. Then the integral of the 2 norm squared is some quartic polynomial in U and U dagger once you take this definition and push it through here. And then integrals of polynomials of U and U dagger are something that you know how to compute exactly. So there's an appendix in the notes about that. And then, so you compute it exactly and you find this. Okay? So that's in words, the proof. If you want the details, you can look in the notes.
Now you have to do this in terms of the 1 norm instead of the 2 norm because your statement about the probability distributions being the same only applies to 1 norm.
Yeah, that's correct. Because you see the typically if you look here, right, the 2 norm can in general be quite a bit smaller than the 1 norm. So you can have situations where the probabilities are quite different, but the two guys are still close in the 2 norm. Yeah. If the dimensionality is large. Incidentally, you saturate this by having sort of maximal mixing. Okay. So let me think of how to say this. So say that, just for intuition, say that A and B are qubit systems, okay, and say that B has 10 more qubits than A. Then we get 2 to the minus 10 here inside of the square root. So in the context of these black hole kind of things that we're talking about, where we were running into entropies like 10 to the 60, then what these things are going to end up being suppressed by is things like 2 to the minus 10 to the 60. Okay, so that's extraordinarily small, and then you would expect the subsystems to be extremely close until right when when these guys are really very close to being equal. Now, let me just say briefly, what did Page actually do? So Page, I don't know, maybe he didn't know about the trace norm, so he studied the entanglement entropy instead. He studied SA. And then he showed under the same assumptions, and basically you can use the same technology also to show this, that SA is log of A. So that's what you would get for maximal mixing. That's log base 2, I guess. Well, let's call it log. I don't want to get into that. Minus 1/2 a over b plus some dot dot dot, where the dot 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 now is, in this version of it, you have to assume that both a and b are large to suppress the dot dot dot. So this is what Page actually showed. I like this version more for two reasons. One is that you don't have to assume a and b are large. You can get an exact bound. And then secondly, as I guess Frank was saying, this is actually a better definition of the closest of the states anyway. You can get into situations where the entanglement entropies are quite different, but the states are the same in the trace norm. Okay. So now we can use the theorem that we sort of sketched to try and figure out what the Page curve should look like. So we can now kill the proof. Okay, so now this is a little bit awkward to say out, but I'll do my best. So the idea now is to look at this decomposition into R and BH, and then apply the theorem. So the idea is that whichever one of these guys is smaller is essentially going to be maximally mixed, which means that its coarse-grained entropy is going to be equal to its von Neumann entropy. Okay, so when the black hole is young, I look at this, I make the division here so that most of the entropy is still in the black hole. Then the radiation is going to be the smaller system, and then so it's going to be playing the role of A here. That means that the radiation will be maximally mixed given the constraints that you would just impose from coarse-grained physics. So what are those constraints? Well, so the radiation is, you've got the black hole here, and the radiation is coming out in the S wave, okay? S wave is L equals 0. So you can essentially describe the coarse-grained entropy of the Hawking radiation by just saying that it's a 1 plus 1 dimensional photon gas, okay? The dimensional reduction comes because it's spherically symmetric. So then its entropy should roughly just be the length of the box, which actually here is the time over which the black hole has been evaporating, times the temperature, which here is just the Hawking temperature. So this is SR, and then technically this is the renormalized one. You can convince yourself that that's the one that you actually mean when you talk about the coarse-grained entropy. So this should start growing linearly here, okay? And the linear growth should continue until we get to some time of order the evaporation time, but less than the evaporation time, where we get to the barrier actually being halfway up here. So the time where the coarse-grained entropy of the black hole is equal to the coarse-grained entropy of the radiation is called the Page time. So you can see that many things in this business are named after Don Page. Yeah, so the temperature is gradually increasing as this is happening, but that's happening over a time scale of order the evaporation time anyway. So once we get to this sort of time scale, then it stops being linear. And then so there'll be some peak, which will be when these two are equal. That's at the Page time. And it'll be fairly sharp. And then at this point, so the whole thing is in a pure state. So the von Neumann entropy of this has to equal the von Neumann entropy of that. And actually, both of them have to be equal to their coarse-grained entropies. It just sort of by continuity, right? Because the radiation is getting bigger and bigger, and its von Neumann entropy is still equal to its coarse-grained entropy. And then sort of there's this crossover, which happens within some sort of order 1 number of bits coming out. That was the point of the theorem.
Can you use the theorem at this point? Because
yes.
of A is not.
Yeah, so there's kind of a mystery region here. But remember, the mystery region is very narrow because, like I said, with the qubits, right? So if you're within 20 qubits, then now the error in the theorem is 2 to the minus 10. Yeah. So there's a very narrow window here where you can't exactly say what's going on, but by continuity you know that it's essentially just got to be the coarse-grained entropy of the black hole that's left at the page time. Okay, that's what sets the height of this. And then now after this, the radiation is now getting bigger and the black hole is getting smaller. And then it's the black hole which plays the role of A in Page's theorem. So now the black hole is maximally mixed. Its entropy, its von Neumann entropy is equal to its coarse-grained entropy. And the radiation field is now the larger system. And its entropy now has to start decreasing. Because the thing is, remember, so in any pure state, maybe I should have said this, it's always true that SA equals SB. Now since the black hole, we've decided now its entropy is just its coarse-grained entropy, that means that the SR also has to be equal to the coarse-grained entropy of the remaining black hole. And we know what that is. It's just the area. And so then as the black hole decreases, then we can just put that in to the von Neumann entropy for the radiation, which means that this comes down again. And this time it's not actually linear. There's some power, which you can work out. So this is for t less than t page. And then SR, renormalized, goes like S naught times 1 minus t over t evaporation to the 2/3 for t greater than t page. So there's some funny power here that it vanishes sort of non-analytically here at t evaporation. So intuitively, you should think of what's going. Here's how you should think of what's going on here. At the beginning of the evaporation process, the radiation is coming out in a sort of maximally mixed state, just like Hawking says. Okay, but eventually. That has to stop being true because Hawking just says the entropy goes up, 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 up forever. So maybe that's worth drawing. So the page curve, as Hawking would have drawn it in 1976, is just like that. And then I guess at some point the black hole is gone, and then you have some fixed entropy there, which corresponds to the loss of purity. So this is Hawking. So in order to have unitarity, we have to turn over. And then what that means is that at some point, the radiation that comes out earlier the radiation was coming out in a mixed state, but it was mixed because it was entangled with the black hole. Okay, that's where the mixing came from. But now after the page time, it comes out, but it has to come out entangled with the radiation which has already come out, because we've got to start decreasing the von Neumann entropy of the radiation. So that's what's happening here, is sort of the Hawking radiation is coming out, and it's purifying radiation which has already previously come out, so that the total von Neumann entropy of the radiation is going down. So that's sort of the reverse end of the page curve. So now just some terminology now. People typically say that for a black hole which is past its page time is called old. Okay, so I'll often refer to that. When I talk about an old black hole, that's what I mean. Yeah?
You apply this to real black holes, right? Because if you start with your photon shell, you have a very special initial state, and then you can't speak about it as a random state in the Page theory.
Oh, good. Yeah, so I should have commented about that. So no, I think actually it should apply even here. And the reason is that, there are some, I didn't really get to say too much about this, but we usually think of the black hole as being a scrambling system, so that if you send in something special in the initial conditions, it won't necessarily look very special from the point of view of the final conditions of what comes out. Now, you can try and be more precise about that, and there's a paper by Patrick and John, which I think probably still is sort of the state of the art in trying to understand, how scrambling are black holes. But I think it seems pretty likely. You have some huge entropic system, and it's sort of mixing itself all together and then occasionally spitting stuff out, that from the point of view of the state at infinity, you shouldn't be able to distinguish it from a random state without, working very hard. Yeah. And in particular, in proving the theorem, I only had to use quartic, I had to use UU times U star, U star. So I didn't even really need to assume that I was integrating over the whole unitary group. I can use one of these two designs that people were talking about earlier, which are simpler subsets of the unitary group, which are generated by polynomially many gates. but which are already enough to make this kind of thing look Haar scrambled. Okay. All right. So I think, yeah, I had some stuff here about, how hard is it to test unitarity, and, what does a typical state look like? How fast do things scramble? I think I won't have time to talk about that. But I do want to say a little bit about complementarity, and then I'm going to try and get into the firewalls. And hopefully we'll finish on time. Okay, so I say goodbye to Paige now. So you'll notice that today I said nothing about the black hole interior. I've just been talking about the S matrix. Stuff going in, stuff going out, is it unitary? That was not an accident, actually, because it's really hard to understand what experiments done in the black hole interior might mean in the language of the S matrix. Because whatever goes on now back behind the horizon, you can't send the signals out to infinity. For this reason, essentially all of the progress that was made on studying quantum black holes in the last 20 years or so was made just in terms of things that you can extract from the S matrix. And there was always this lingering issue that nobody was really able to say very much about how do you actually describe the region behind the horizon. There was one attempt to grapple, though, with the kind of issues that might arise. And this is this was in the mid-90s. This is some thought experiment, which is due to Lenny, my advisor, and Laris Therlasius. Okay, so here's the idea: is you imagine, so you've got this. So now I'm going to draw an interior again. And then so when the black hole is evaporating, sometimes people like to stick this part up here, although it won't matter too much for what I'm saying. So then here's the shell that I made the black hole out of. And then the idea is that, okay, so to describe what's going on back here, what's the first thing that you would try if you just looked at this? I think what you'd probably do is you'd say, well, you can imagine some spatial slices here, and at least sort of in perturbation theory, we should be able to talk about degrees of freedom on the slices as long as we're careful to, pick the right gauge on this kind of thing. And then you could just imagine doing Hamiltonian evolution up to some slice. Maybe I'll put it up higher. Actually, I think I even want the slices to be in different colors. So maybe I'll make this one red, and I'll make this one blue. And then you could imagine that there's some at this time, or there's some configuration of fields on this slice. It's a pretty boring configuration of fields because the only thing that's on it is this inflowing matter shell. And then there's some configuration of the fields on this slice up here. And then the issue that these guys raised is that if you believe that the evaporation process is unitary, and you think that you can make sense out of the degrees of freedom on these slices, which by the way is, not clear, right? now we're going beyond the S matrix. We're saying, that there's some sense in which there's really a quantum state on this slice. Then you can have cloning. You can violate the no cloning theorem of quantum mechanics. And the idea is very simple. So, you've got your ingoing shell here, and you can imagine just attaching onto that ingoing shell some quantum state of your choice. You just throw in some quantum memory or something that's in some quantum state that you like. And then, so here there's one copy, because you just threw in one. So then up here it'll still be there, because the shell is just coasting along. It doesn't know that there's anything particular going on. But then if the evaporation process is unitary, then eventually this information about the quantum memory that I threw in has to come out in the Hawking radiation. And I can push this slice late enough that that Hawking radiation has already come out, that it's actually already come out. Now, how late do I have to push it? Well, so remember from our discussion of Page that up until this Page time, the state of the radiation is just maximally mixed. So it doesn't have any quantum information. But then after this, it starts having information. The entropy starts coming down, and you start learning about what you made the black hole out of. So, at a minimum, you would have to push this up past the page time. But, there's nothing to stop me from doing that and still drawing this slice. And then now it looks like I've got a cloning machine. So that's bad. So that means that there can't be sort of linear unitary evolution of some quantum state between these two slices. Yeah.
So I thought the no-cloning theorem is based on the linearity of quantum mechanics.
That's correct.
But this might not be true if you have a quantum theory of gravitation where it gets nonlinear.
Yeah, but remember the whole philosophy of why we wanted the evaporation to be unitary is that we wanted gravity to be consistent with quantum mechanics. So if you're willing to have gravity violate quantum mechanics, then life would be so much simpler if we would just go back and say Hawking was right and that there's information loss. Yeah, so we're trying to not have that. We're trying to arrange to have the information come out, but not have not have quantum mechanics be violated. Yeah.
So you said you have to go at least after the page time.
Yeah.
But of course that information you set in might come much later. Is there any argument why it can't come?
Yeah. So Patrick and John studied this in their paper. So what they said. So the version I presented here is the version that Lenny and Thorlasius talked about, where you send in the information along with the initial shell. But one obvious way to try and make it come out faster is to just wait until you're already past the page time and then throw in the information, and then maybe it'll come out faster. And actually, what Patrick and John argued is that it will come out faster, and it's a quantitative thing which you can think about. How fast does it come out? And I'm going to say more about that in a sec. Okay. So what these guys pointed out, though, is that at least in this setup, in the original setup, nobody can actually see the cloning, because you can wait up here. You can wait out here, wait until you get the Hawking radiation, and then you can jump in and try and see this cloning over here, but you can't. You're prevented by causality because you hit the singularity long before you're able to see what's going on here. Now you could say, well, you dummy, why didn't you just draw the slice like that? So that then it looks like you can see back there, and then it's harder to argue by Penrose diagram against that. But what you find if you do a little bit beyond the Penrose diagram is that if you do that, then it's true that the information was here at some point, but it's extremely redshifted from the point of view of someone who jumps in later because of the gravitational redshift we talked about, and so essentially you won't be able to see it unless you encode it into some extremely short distance sort of Planckian, super Planckian kind of memory, which we probably think doesn't exist. Now, in the version where you throw it in here, you're not even close to being able to see it. In the version that Patrick and John studied, you're much closer to being able to see cloning by doing this kind of thing, but you just barely can't. Okay, and I won't go through the details of that, but you should read their paper because it's a fun paper, and the arguments are not that hard. Using the tools we've introduced, you could understand it pretty easily. Okay, so what these guys suggested is that maybe that's fine. The issue then, the problem here is not that quantum mechanics is violated. It's that we asked quantum mechanics to do something which it had no business doing. We asked it to give a description of the state on this entire slice, even though nobody can see everything on this entire slice. So maybe our problem was just that we asked it to do too much. And then maybe maybe instead of asking for a sort of global description of this slice here in terms of quantum mechanics, we should just ask that any particular observer who jumps in at some time, that just within what they can see, that quantum mechanics is consistent. And shouldn't that be enough? Why shouldn't we? Should we ask for more? So that idea is often called black hole complementarity. Now you might say that this is sort of maybe this is getting a little too philosophical for you. If there's a contradiction, there's a contradiction. If you can't see it, that's your problem. It's not the theory's problem. I'm sympathetic to this, but I just wanted to say that there is at least one historical example where this was a good way of thinking about it, which is the uncertainty principle in quantum mechanics. So Heisenberg has this convoluted thing which you read about in your textbook, where he says, you try and measure the position of the particle, but then if you do that, you screw up its momentum, and if you try and measure the momentum, you screw up its position. And for operational reasons, you just can't measure both. So that's kind of like this. Maybe there's the stuff here and there's the stuff here, but somehow you can't look at both at the same time. And now a classical physicist could have said, well, that's your problem. It's a particle. Of course, it has a position and a momentum. That's what particles have. And I'm sorry that you're not a good enough experimentalist to figure out how to measure them. And that would have been a wrong argument, right? I mean, that would have been a profoundly wrong argument, because indeed what was going on was that the classical physicist was using the wrong definition of particle, and the kind of thought experiments that Heisenberg was thinking about were really important for the consistency of what actually turned out to be the right description of the particle. Now, of course, once you then know the right description, you can forget about Heisenberg's arguments, which is what we usually do. But sometimes this kind of thinking is actually suggesting a new kind of framework, that you should, and you should sort of ignore these kind of operational constraints at your peril, because you might be putting your biases in about the structure of the theory when those biases may not be true. Okay. So that's all I was going to say about complementarity. Now, let's see. So we started 10 minutes late.
Yeah, so
What?
10:40.
10:40, is that a reason? Would I be allowed to say do 10:50, or is that a... I can cut things out, so 10:45? I should have chosen a higher...
Well, you didn't specify the day or the AM.
That's true. That's true. Okay. So yeah, I think maybe I'll just very briefly comment. So there was. Why did we all decide that unitarity was correct? So I was originally going to talk about ADS-CFT, and I'm not going to because I don't have enough time. But it's something that you should know about. So I just want to say a very brief. There are two things that happened in string theory in the 90s that convinced almost everybody that black hole evaporation has to be unitary, and I would be morally remiss if I didn't mention them in this talk. So one is that in string theory, people were actually able to compute the entropies of black holes from counting microstates. They were able to, so when Jacob was talking about microstates, he just had some sort of idea that there should be microstates without any explicit description of what they are. But in string theory, actually, so if you just want to compute the scaling with the area, then there's a very large number of black holes where you can really count the entropy in terms of, excitations of strings. And if you want more than the scaling, if you want more than just that it's proportional to the area, but you actually want to get the coefficient, the 1/4, then there are special cases where, which have, large amounts of supersymmetry, where you can, in fact, count the states precisely enough to get that coefficient right. Okay? And that really, that's the microstates are really there in front of you, and they can't be denied. And I think that was a big sort of initial step in causing people to really, converge around unitarity. Now, the second thing was then, of course, ADS-CFT, which is even better because now that's a framework of, an exact theory of quantum gravity. I'll just draw the Penrose diagram, since it's like a box. So you have some origin of polar coordinates here. You have some spatial boundary here. But light can get out to the boundary and back in finite time. So it's like living in a box. But then you're also able to send things in from the outside by fiddling with the Hamiltonian. And then you can just set up exactly this scattering experiment that I'm talking about. You can send in, some shell. it can evaporate into photons at the you can catch them at the boundary, and the whole process is explicitly described by unitary evolution in some quantum field theory. And there's really just no room to fight about it. I mean, there are some people who still quibble with aspects of this, and in the notes I'm planning on putting just some comments aimed at those people. But I mean, I think this is essentially almost incontrovertible evidence that at least it's possible to have the formation and evaporation of a black hole be a unitary process. Okay. Yeah?
There's a phenomenon called entanglement locking that tells that if you have an entangled system, you can lose almost all the entanglement by just losing one qubit. And I'm wondering whether this can apply here also for resolving this paradox. Because you could essentially say one qubit can be lost when the black hole finishes evaporation. And without this one qubit, things change. I don't know.
No, I don't think. Yeah, that must be in some special case, because generically what happens is, if you have some complicated pure state and you lose a qubit, the entropy increases by log 2, well, or by 1 if you use the base 2 log.
That's for mixed state. For mixed state, if you have mixed state of the system, then you can never. Yeah, but for pure states, it doesn't hold.
Yeah, I think that can't work, because a pure state can't turn into a maximally mixed state by losing 1 qubit. Yeah. Okay. So, I was lazy and didn't print my notes, so I apologize, but I'm going to look at my phone for the... okay. So, now we've settled the information paradox. Great. But I want to come back to the interior now, because, there was this one kind of contradiction that we ran into, and we thought, well, maybe it's resolved by complementarity. This isn't really satisfying, right? I mean, I didn't actually give you a theory of the interior. I just said, oh, well, there's this one kind of problem you can run into, and it seems to be okay. But, who knows? Maybe later someone else will come up with another problem that you won't be able to resolve in this way. So maybe this idea isn't actually consistent. The only way, usually, you can know that some idea is consistent is if you have an example. If you have some theory that, is consistent and is, has this property that it sort of describes quantum mechanics only for individual observers. People sort of, said, okay, yeah, it would be nice, but then they didn't really think about it too much for the next few years. But then recently, it's been argued, I think fairly compellingly, that at least the original version of black hole complementarity can't be consistent. Okay, and that was what led to all the, 150 papers in the last year and a half, all talking about the black hole interior. So now I'm going to try and get into that argument. Maybe just a brief historical comment.
What is this complementarity?
Yeah, complementarity is the idea that, so without a theory, it's hard to give it a precise definition, but roughly it's the idea that if you just focus on what an individual observer can see, that unitarity of black hole evaporation doesn't require somebody to see a violation of quantum mechanics locally. If you write down these global slices, then you can have violations or what look like violations, but it doesn't matter because that's just the theory doesn't really have this structure. Yeah. But it is kind of vague, so you shouldn't feel like it's something when it's well defined. And in the literature, people call different things complementarity because it's okay. So the argument that I'm going to present is due to Almeri, Meroff, Polchinski, and Sully from 2012. It's called AMPS usually. I should say, though, that the ingredients in the argument have a longer history. So the contribution of these people was really to just sort of assemble together these things that were known and point out that they really directly are attacking black hole complementarity. The other people whose work was important leading into this are Steve Giddings, who already back in 1994 had expressed some concerns which were similar to what ended up going into this. And then also in 2011 he said some more about it. Then there's this guy Braunstein, who probably you guys know better than me, from England, who in 2009 sort of managed to, without knowing too much about black holes, kind of get himself sort of confused in the right way to lead him to the same kind of problems that these guys were talking about. What they called firewalls, he called energetic curtains.
In
and-
both cases, we learn F is better.
Yeah, definitely. Yeah. These guys should have talked to Rob. And then I think actually the main driver, and I know the person who by continuously harassing these people provoked them into doing this work, was Samir Mathur, who I think it's 2011. So he really the quantitative heart of this is due to Samir. In some lecture notes from here, it's a use of strong subadditivity that we're going to see in a few minutes. Well, in any event, that's the history as far as I can understand it. So now let's get to the argument. So the goal of AMPS is to take all of the moving pieces of the black hole information paradox and put them all into the past light cone of one observer, to make it so that that one single observer has to see some paradox in order for information to get out. And so that was what was not true here, because you could either ride in the shell and you could see the information here, or you could stay out and see the information here, but you couldn't see both. What AMPS suggested was instead you just look at somebody who jumps in, okay? So here's the person who jumps in. I guess I tend to call the person who jumps in Alice. Poor Alice. So what Alice can see is all below these light cones here, because anything up here or anything out here is invisible to Alice. So then the goal is to get a paradox where everything is below these light cones. Okay, so now maybe I'll try and make this a dash dot 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 dot. So the horizon is the dashed line. This black lines are sort of Alice's horizon. She can't see beyond these, or white lines. These white lines. And then this white line is Alice. Maybe I'll make Alice blue or something. So then we can, now rather than imagining that there's some quantum state on this whole slice here, we're just going to imagine that there's a quantum state on some red slice here that stays in Alice's past light cone. And then we're going to think about the properties of the field theory degrees of freedom on this slice, and argue that in order to both have Alice smoothly fall through the horizon and for the evaporation to be unitary, that the state on this slice is going to need to have impossible properties, that there's no state that we can find which does everything that we want. So first let's talk about what she needs in order to have a smooth horizon. So now I'm going to introduce some subsystem A on this slice, which corresponds to some of these modes that I was talking about before, but the modes behind the horizon that are right moving along the horizon here, and some modes that are left moving along the horizon here. Now to get intuition for these modes, I'm going to go back to Rindler space, because we did a lot of Rindler space in the previous lectures. So the Rindler decomposition. So you should think of Alice as being analogous to this person over here who crosses the horizon there. And so remember I argued before that the entanglement between things here and things here was necessary for Alice to be able to smoothly cross the horizon. And that if these things get disentangled, then there's a firewall. Okay, in quantum field theory, that's a true statement, because we understand quantum field theory well enough to just see that explicitly. Now, this region down here isn't really part of this geometry, because it's sort of over in the other exterior that we removed when we went to the collapsing geometry. But we can just trace, we can easily fix that by just tracing these modes up to here, and these modes up to here. And then now there's a mode in the vicinity of where she actually jumps in, and another mode here in the vicinity of where she actually jumps in. And they still need to be entangled because they're just related by evolution. So if you have, if I have a system here and it's evolving, and I have a system here and it's evolving, then the statement that they're entangled can't be changed just by the local evolution. So that means that A needs to be entangled with B on this slice in order for Alice to not see a firewall. Okay. So smooth horizon. And I'll just write it like this. So I don't know, I just made this symbol up, but it means that A is strongly entangled with B, as we found in Rindler space earlier in the lectures. Okay, so that's the constraint imposed by the smooth infall. And so far that's fine, but I now have to use unitarity as well. Okay, so this is where I'm going to make contact with the first half of the lecture. So let's think about so these modes. There's these modes B here, the modes going along here, and then there's the early radiation out here R. Okay, where R is going to mean the same thing that I was talking about earlier. So we can imagine that this decomposition I was doing into B and R. Imagine it happening like somewhere around here, okay? So then here's R, and then here's BH, okay? Amusingly now, B here stands for black hole, and then also for this mode here, but it's okay because this B is part of the black hole, and then eventually it's radiated out into the system. So there's no clash of notation, although it may be a little confusing. So now the idea of amps was to say, let's wait until the black hole is old and then have Alice jump in. But when the black hole is old, this BH system is maximally entangled with R, okay? Because R is now much bigger than BH, so then if we just look at the BH, it's in a maximally mixed state, which is all of that entropy is entanglement entropy that's coming from the entanglement with R. But if BH is entangled with R, then any subfactor of B also has to be maximally entangled with R. So one way of thinking about that is if I have the identity density matrix on B and H, then I could imagine splitting this region up into HB, the part that comes from the evolution of the modes here, times HH. So now we're really getting crazy. Where H now stands for horizon, or stretched horizon. And of course and this is really working great because BH also stands for Bekenstein-Hawking. But it's all consistent. So you're right. This is just the piece of this which comes from the mode here that I'm interested in, and this H is just the rest of whatever is in the black hole from the point of view of the person outside. And then I can use my mastery of linear algebra to discover that. So then that means that B itself also needs to be entangled with something in R. Now, more carefully, it has to be entangled with some subfactor of R, okay, which is just some generic statement about entanglement, right? You have this is essentially the Schmidt decomposition. So if I do this decomposition into B and H here, and I have some pure state where B and H are maximally entangled with the radiation, then okay, I'll put in some normalization just to look fancy. Then there's some basis. So this is just some basis I happen to pick. So this is the product. If you like, we can write it like that. There's some basis for the radiation where the quantum state just looks like this. And then we can think of the B here as being a subfactor of R, which I'll call R sub B. Okay, it's just some subfactor of the radiation, and it has the property that if you look at the joint state of RB and B, it's close to pure. So B is purified by R sub B, and then that is necessary to have unitary evaporation. So remember, this followed from Page's theorem, the statement that this is entangled with that, and it required that the evaporation was unitary. Now, this is interesting. What? Yeah, that's so. Remember, now the black hole is old, so the coarse-grained entropy of the radiation is larger than the entropy of the black hole. So I just reflected that by picking some particular state here to fill out the rest of the coarse-grained entropy. Yeah, just think of it as a bunch of zeros if these were qubits. Okay, now this is kind of mysterious because I would have said, and in fact I even did say in a paper, that Alice jumping in here can't test unitarity because she doesn't get to measure the S matrix, right? I mean, she jumps in and she gets annihilated in the singularity. So you might have thought that unitarity shouldn't put any constraint on what Alice can see. But you see, by using Page's theorem, we've managed to sort of pull back the unitarity of the S matrix into a statement about this slice here, which is actually accessible to Alice. We could imagine, she flies around playing with the radiation for a while, then she jumps in and looks at B, and causally, at least, there's nothing to stop her from verifying this entanglement between B and RB, and then jumping into the black hole.
But you said before, because of redshift, it would maybe some very short distance.
That's no longer true here, though. I mean, because we're doing a different experiment now. I mean, that was the experiment where you throw something in and then you jump in a long time later and look at it. That's not what I'm talking about now. I'm just, you fly around outside for a while and then you jump in. And the B that you pick is the B that's right there when you actually jump in. It's not some B which is down here. And similarly, the A is not some A which is down here. It's some A which is sitting right where you actually jump in. And it's not redshifted. It's the important A and B that you pick.
Its proper time is the same as yours.
That's right, yeah. Yeah. It's just the mode here and here in the Rindler decomposition. Okay, and now this is bad, okay? So this violates the monogamy of entanglement, which I guess Frank talked a little bit about in his talk. Now, rather than just saying that it violates the monogamy of entanglement, so this is the part that we can get from Samir, we can actually write it out. So we can look at this strong subadditivity applied to these three systems. So SB plus SAB R sub B has to be less than or equal to SAB plus SB R sub B. Okay, so this is some fact which is true in general about density matrices. So in particular, I don't even need to assume that I'm not necessarily assuming that the state on this red slice is pure. Although I mean you may or may not want to, but we don't have to. So now we can use some more fun information theoretic tricks, and actually the intermediate sentences I say here, I also asked you to check on the homework in case you haven't seen this kind of thing before, although I guess most of you have. So first of all, let's assume that there's unitarity, because that we decided 20 minutes ago that because of ADS-CFT and string theory that the evaporation has to be unitary. So then this one has got to be true, that B is entangled with R sub B, and that means that this is close to 0. Let's just say it's 0. Okay. Now, if this is close to 0, then you can convince yourself that this then is just SA. Intuitively, it's kind of clear. If these guys are pure by themselves, then the ABR-RB somehow should just be like the product state of B times, the BRB state times rho A. Okay, and then so the pure state here won't contribute to the entropy. But then what have we learned? We've learned that the mutual information between A and B is negative or 0. Okay, but That's interesting because we also know that the mutual information is greater than or equal to 0, just from the definition of the mutual information. Well, apparently that means that it is 0. Okay? But that's bad because, as you also prove on the homework, in case you didn't already know, this implies that rho AB equals rho A times rho B. So it's a product state. Which is inconsistent with this, obviously. So apparently having the evaporation process be unitary, if these assumptions are correct, it says that these modes inside and outside the horizon have to be completely uncorrelated, which means there's a firewall. So that's the AMPS argument from the 2012 paper. It's actually not quite the way that they presented it. It's the way that I like to do it. I guess Patrick and I wrote it this way in our paper, but the main ideas are just from here. You know, we're just being pedagogical and trying to state the assumptions more clearly.
So in this case, the monogamy of entanglement is encoded into the strong subadditivity.
That's right.
What was the argument you missed when you argued that Alice couldn't do the experiment?
Yeah, well, so this is a different experiment, right? Like the experiment we were talking about before, you tried, the information you extracted was some information about something that you threw in. So the new thing here is that instead you extract information about something that's coming out. So instead of trying to decode from R, you know, I don't know, a diary that you threw in here, that's what Patrick and John were talking about. You instead decode from this, you know, something which is the state of some mode which is coming up along here. So that's the new idea.
Like if you said that you had written a paper saying this wouldn't work.
Oh, yeah. So yeah, I had some argument that it was hard to measure this mode. Well, I've written 2 papers. One I'm going to talk with Patrick. I'm going to talk about in a minute, and that one's not wrong. Although there was a paper on the archive today about it. But, I'm happy to talk about that afterwards. But, okay, yeah. So no, yeah. I at some point I tried to argue that that it's hard for Alice to confirm this because it's hard to measure B, but I think that argument doesn't really hold up. Yeah.
So in this construction of this paradox or whatever,
Yeah.
you assume that A, B, and R stays in the lower energy effective field theorization.
Yeah.
They don't go beyond the Planck scale.
Yeah, that's correct. Yeah, and it seems to be the case. I know you guys have some argument otherwise, but I haven't really managed to understand this argument yet. Yeah.
This happens for every observer you might run into the black hole, but there is no assumption about the time.
Well, I had to assume the black hole was old in order to get this entanglement, so you have to jump in after the page time. But other than that, no, nothing other than that. Yeah. Yeah. So I was being a little bit vague here. So the idea here is that if you think about this from the point of view of someone from the outside, then it's kind of natural to want to split up. So I previously had done this decomposition of BH and R, but I did it at infinity where it's really rigorous. But now you kind of are very tempted to sort of pull this back into the bulk and understand the decomposition at some finite time. And then you're tempted to sort of split the black hole into 2 parts. The part which is really up against the horizon, a Planckian distance away, and then the modes that we talked about a lot earlier, I guess yesterday, the modes in the atmosphere, the modes in the zone. The guys that are confined by this potential barrier we talked about yesterday, in between the potential barrier and the horizon. So those modes are the ones I'm calling B, the sort of Rindler-type modes that are behind the barrier. And then H is kind of the stretched horizon. It's the stuff that has been scrambled in and you can't see it anymore. And it's where most of Jacob's microstates would be in this picture of things. They'd be up, sort of carried in the stretched horizon. So then I just, that intuition I was using to decompose BH into the thermal atmosphere and the rest. And then B is just, little b, this is some complete basis for the atmosphere, and this is some complete basis for the stretched horizon. Yeah, so that's one of the subtleties. So yeah, you should probably think of them as being renormalized. Now, you can convince yourself that that's okay by the following argument. So you notice each region appears an equal number of times on the two sides. So A appears here once on both sides, B appears twice on both sides, RB once on both sides. So if you do these subtractions, then what this subtraction is doing is it's just subtracting something proportional to the area, like what Rob was talking about. And then, so the divergent pieces will cancel on the two sides of this. So then it should still be true for the renormalized entanglement entropies. Yeah. Yeah.
Some cool theories like CFT where you can show all the whole process in filters. So is that a final problem there, or is that
Yeah, that's a great question. So the short answer is yes. But the thing is, unfortunately, in ADS CFT, we have the same problem that I mentioned here in Minkowski space. We're very good at describing what's going on out at infinity, sending stuff in, stuff coming out. But we don't really understand ADS CFT well enough to know how to describe things that are behind the horizon. In particular, we don't know how to describe this A. Okay? And actually, that's a nice segue. Let's see. Okay, maybe so. I'll say I have 10 minutes left. Or no, I have 5 minutes left. Okay. So then I'll just say briefly in 1 minute. Yeah, so there are various arguments, which I didn't have time to get to, that the things like the creation and annihilation operators for these A modes can't really be realized as linear operators on the Hilbert space of the CFT and ADS CFT. So there's some sort of there are interesting paradoxes about how exactly the interior emerges in ADS CFT. I expect that there's going to be a lot of talk about this at Weitzman next week at the conference for the people who are coming. But I just don't have time to say more about it now. And of course, the reason I don't have time is because I have to say at least something in this lecture is about something that I actually did that wasn't wrong. So I'm going to close by saying, is complementarity dead? Should we give up and accept the firewall? Well, there's something I sort of was sneaky about in this discussion, which is that when I wrote down this state, I told you that there's some basis of R where the state looks like this. But I didn't tell you what that basis is. And it's actually going to be a horrible basis because in terms of, a physically sensible basis of the radiation, like, there's a photon here, there's a graviton there, this kind of thing. That's not going to be the basis where the state looks like this. If we want to work in that basis, then there's going to be, I left this space here, some gigantic unitary transformation acting on the radiation, which scrambles the information. Okay? If black holes scramble, then that should be true. The information should come out in a complicated way. Which means that if Alice, the infalling observer, wants to decode this entanglement, she really wants to see it. So remember the goal here was to make the monogamy violation be observable to somebody. Then she has to figure out how to act with UR dagger on the Hawking radiation. If she can't do that, then she can't confirm this entanglement. So what Patrick and I did was we studied the computational complexity of acting with UR dagger. And what we argued is that, well, it seems like there's pretty decent evidence that implementing this UR dagger takes time, which is exponential in the entropy of the black hole. Under the usual assumptions of, which probably in this room I don't have to justify too much, which is that, the way we quantify the complexity of quantum computations is by using circuits and this kind of thing. You can imagine sort of more exotic things which don't seem to help. So in terms of Scott's alphabet soup, the complexity theoretic statement here is that there's some complexity class which is called QSZK, stands for quantum statistical zero knowledge. You know, even though Scott introduced more complexity classes than I did coordinate transformations, he still didn't introduce this one, although I'm sure he could have. This is the class of problems where if you had available to you some all-powerful deity who you could send, you know, quantum states to, and he could do something to them and send them back to you, then he could and he could do arbitrary manipulations of them. Then he could statistically convince you of the answer of the problem without giving you any information about this actual solutions. That's what the zero knowledge means. So this is one of these bizarre things that, I guess it actually comes out of cryptography, these kinds of things, you know, where, you know, you have some adversary and you want to give the adversary as much power as you can, and then you still want to see what you can sort of get and hide from the adversary. So thinking about that kind of thing led to this class. So what Patrick and I argued was that if you can generically invert this matrix in polynomial time on a quantum computer, then the circuits that you use to solve these problems have to be small, polynomial size. And that's surprising because the definition of this class involves an all-powerful prover who can do exponentially large quantum computations. So if there were small circuits available to solve these problems, then, well, that would be surprising. It'd be like saying that this resource of this person who can do, you know, exponentially long things isn't actually necessary. So I guess from a complexity theoretic point of view, that's surprising. Yeah.
But what if somebody knows the S matrix of the black hole? What if somebody knows everything?
Yeah, I'm assuming you know that. So in the definition of the problem, we grant you complete knowledge of the S matrix.
But can't I know what's going to happen to the basis then?
No. No, it's not. I mean, so I mean, it's the same kind of thing, right? So knowing the S matrix doesn't necessarily mean that you know what's the right description of the interior, right? So I mean, I'm trying to make an operational statement, and then we can think about what it means from the point of view of symbols later. But in this setup, you do know the S matrix. We assume you know it. The question is just, if you know it, can you use that information to invert this in polynomial time? And the answer is no. Okay? Or at least seems unlikely. Yes, now Scott has actually generalized our result now. I don't think he's written it up yet. To show that essentially, assuming that there exist one-way functions which can't be inverted, so for the computer scientist, I guess you know what that means. If you assume that, then you shouldn't be able to generically do this. So if you could, in other words, if you could generically, you know, given some state that you prepared in some polynomial time, you know, using the exact quantum gravity dynamics, if you could do this inversion in polynomial time, then there would be no secure one-way functions that were secure against sort of quantum computer attacks. So it's an amusing argument. So let's say that that's true then. Then we could imagine that there's a new kind of complementarity. So there's somebody who stays outside, who sometimes I like to call Charlie, who can test the unitarity of black hole evaporation, because he can just wait. He can look at B, he can look at RB, and he's got all the time in the world because he's sitting around outside, and he can confirm this entanglement. But he can't see A because A is behind the horizon, so he can't see a contradiction. That's the usual story. But now if we think about Alice, well, the black hole is going to evaporate in polynomial time. In fact, it's going to evaporate in a time which is of order the entropy to the 3/2. So if Alice, so of course Alice can jump in and she can see A and B and she can confirm this entanglement. But if she wants to check this entanglement, she has to do this exponentially long quantum computation. And by the time she's done, the black hole will have already evaporated. And she won't have time to jump in and try and check the AB entanglement anymore. So if you're willing to accept this, then it seems like, at least in principle, complementarity is still alive with this additional restriction. But I really want to emphasize this. That doesn't mean that I think that the problem is solved. Because the whole problem we learned with complementarity is that if you don't actually have a theory, then you'll never know if someone else isn't just going to come up with some other inconsistency later, and then you're going to have to deal with that one too. So, you know, Lenny and Thorlasius had some contradiction, which was resolved by you know, some sort of restrictions on, you know, causality and this sort of thing. And now these guys have a new contradiction, which, you know, if you believe our arguments, maybe you can push into unobservability. But, you know, tomorrow someone else will come up with another thing, or like I said, today already on the archive there's a claim that there's another thing. I have my own issues with what they're saying, but still, I mean, even if this one doesn't work, maybe another one will work. So, you know, I think, you know, we're back to the now, in my view, we're sort of back to the status in the mid-90s, but that was bad, right? I mean, so we need an actual theory of the interior, and then, you know, perhaps that theory will take advantage of this kind of loophole in its own consistency, but until we have that theory, we don't understand this problem. You know, I encourage everyone to think about it. Certainly it's a hard problem. It's a fun problem to think about. And finally, I'd like to thank the organizers. I've had a fun time here talking to everybody, enjoying my time in Jerusalem. So I appreciate it. Thanks.